Hello, everyone, and welcome to the Pi and AI session hosted by Mozilla Campus Club of SCSL. We're excited to have you all here today. So we have a fantastic session planned for you all. Today's event is dedicated to computer vision, one of the most exciting areas of AI right now. And we have a brilliant speaker lined up to guide us through the fundamentals. So let's kick things off by introducing our amazing speaker. Ms. Aqsa Kauser, who is the head of AI at Red Buffer and a Google developer expert in machine learning. With her wealth of experience, she'll be providing us with some invaluable insights in breaking into computer vision. So now let's get into the event agenda. Briefly, we'll start with the presentation and followed by the hands-on session. And then we'll give you a chance to ask questions if you have any. So yeah, without taking much time, let's start. Ms. Kauser, the mic is over to you.
Hello, everyone. Can you all hear me?
Yes, we can.
All right. Okay, that sounds good. Okay, so let's dive in. Just let me share my screen and then we should be good to go. So let's get started. So I am Aqsa Kauser, currently head of AI at Red Buffer, which is a services-based company based out of Islamabad, Pakistan. At Red Buffer, we basically provide AI services, machine learning services to clients in Pakistan and abroad in the US, Europe, etc. This session is focused more on computer vision, but since it's more of a beginner session, I would like to address some of the basics of machine learning. So we'll start off with what traditional programming is. So traditional programming is where we have rules and data that goes in and we get some answers, right? So we define what rule there needs to be. When we talk about machine learning, what happens in machine learning is that we have answers and data, and the machine learning figures out the rules by itself. So moving forward, we'll see how this works. Overall, artificial intelligence is the main border, and machine learning comes under artificial intelligence, and deep learning is a part of machine learning. So for example, we have inputs, as you can see on the screen, and we have the desired output that we want, right? So we have 0, 1, 2, 3, 4, and the corresponding output that we want is 1, 3, 5, 7, and 9. So there has to be some mapping that will map the inputs to the outputs. So when we talk about mapping, if just you guys out there, and if you think on it for a second, what could be the mapping that would map from this input to the outputs that we want? I want 0 to be mapped to 1, 1 to be mapped to 3, and 2 to be mapped to 5, and so on. So if we put some thought and some time on this, like a few minutes, then we can easily come up with the following solution, which is y is equals to 2x plus 1. So when we are trying to think of, without doing the maths and the formulas, and we're just, letting our brain, doing some brainstorm and just trying to figure out, then there's kind of like this iterative process that's running in our head, right? Okay, we may start with x plus 1, we may start with, and then we may go with 2x and then think of, okay, no, it's 2x plus 1. It's a slight iterative process, which has, where, our feedback with our brain is a lot more fast. And since this is a simpler problem, we are able to come up with the solution. But what if we have something like this? Right? We have an input and we have an output. And what we basically want to do is we want to understand, okay, what would be the output value for an input value of 38? Similarly, if we come up with the mapping, then this is actually the Celsius to Fahrenheit formula, and this is how what it looks like. So if I want in traditional programming, what I would do is I can convert this into a function. We have the value of C that goes in. I already have a defined formula and I get the value returned. So input, algorithm, and output. But what if I don't know the formula, right? What if the problem is way more complex and it's not the Fahrenheit formula, it's something else, and I just have the input output data? Then what goes in here, right? What machine learning actually does is it takes the inputs, it takes the outputs, the corresponding outputs, and it figures out the algorithm or the mapping by itself. That's why we say that machine learning learns from data. So for example, in this case, it would learn from the data that was given, and then when we give it 38, it would be able to predict the value 100.4 for it. So in neural networks, which are the simple machine learning models, we have input layers, hidden layers, and output layers. So, and these are things that, these are small models that we can also build in TensorFlow, and we have a value going in. Then we have some values that the model learns. For example, in this case, the W and the B, those are the values that the model will figure out itself. As you can see, eventually this actually forms this equation. And in simple terms, this would actually form the equation that we're looking for the Fahrenheit. But as it gets more and more complex, you have more and more values that you can learn, and they're all forming more and more complex functions. For example, this node and this node and this node. So if you can see, they're all forming these complex functions. In A1 is actually opens up into this, A2 actually opens up into this, and A3 then is a combination of A1 and A2. And all of the W's and the B's that you can see here, those are the values that the model learns. At the end of it, it's basically a lot of math that's going on behind the scene. Now let's step into linear regression. Linear regression is from traditional machine learning, and it's a very simple but very powerful method that's used for predicting when we have linear distributions. For example, we have price and we have square feet, and we want to predict price for houses. And one of the things that we know, and this is the data basically that we have, so we have square feet and then we have the corresponding price. But obviously this square feet we don't have the corresponding price for all the square feet on this line, or moving forward if we extend this, or the middle values where we don't have dots. So we don't have the corresponding prices for all of those square feet. But we want to have some formula that can help us find price for different square feet. So one of the things that we can just do is, okay, we can just figure something out ourselves and just come up with some line of best fit ourselves, and then just use that as an approximation. In linear regression, machine learning is kind of trying to do something similar. So it's trying to find the best fit line. And how is it basically doing that? So you can, as the machine learning model is training, you can think of it as, this line being moved up and down. And at each iteration, the model is trying to judge whether or not this is a good line or it's not a good line, right? That it has formed. Now, how does that happen? That happens by the model figuring, looking at a cost function or a loss function or error function. So these names are used interchangeably in some cases. And so let's just say, okay, we're looking at the error. So for example, this is what the actual square feet price value here was actually somewhere here, but our line predicted here. So we have this error. Then we have this error, we have this error, this, and these errors, different errors. So we can combine all of these errors and then see, okay, what's the total error that we're getting for this line? And that's something that will be done for all the different lines that the model is trying to predict. And eventually it would come up with a line that it feels has the minimum error, and then that would be the formula that we are getting. So this is what we get when we're talking about linear regression. We want to predict a line, we can use linear regression. We have some error that we can look at. But what do we do when we basically have no discrete, we don't have continuous data. We have basically, discrete data. We have ones and zeros. We have classifications, for example. For example, we want to detect whether an email is spam or not spam, or whether a tumor is serious or benign, or whether a transaction is fraud or not, right? So what do we really do in those cases? So if we think, okay, let's just use the same linear regression formula, and we take the tumor example here, and we have these tumors with sizes where, we're getting, these are not serious. And then we have tumor sizes, greater than a certain value, which are basically serious. And when we apply linear regression, we will get a line something like this. And maybe we can say, okay, let's threshold this at 0.5, and anything greater than that is serious. Anything less than that is, not serious. But what's the issue here actually? So the issue here is, for example, if we also have in our data a tumor of this size, which is an outlier here, then our whole line of best fit would actually shift, because it's based on the error. It's based on different points of how the distance of different points from the line. And the model will actually come up with a line like this, so that the distance from this point is also less. So this actually shifts our 0.5 threshold here, and now we are misclassifying 3 of the serious tumors. So linear regression is not a good solution for cases where we have classification problems, where we have zeros and one problems. So in this case, we come up with what was basically the solution for such cases was logistic regression. So now logistic regression, what it does is it tries to find the separation boundary between the data. Instead of finding, the best fit line, the line with the least error from all points, it actually finds the best fit boundary between the 2 points. So these are some examples of how it finds, what are the best fit, boundaries for different kinds of data that logistic regression finds. So how does it, so moving on, we'll look into something that's called a sigmoid function, which forms the basis for neural networks. So sigmoid function actually is a function that gives 1 for values where, you're getting greater than 0.5, and 0 for values where you're getting less than 0.5. So you have inputs, and all of these inputs would go into a function, and then it goes into the activation function, and we get some binary output. So this activation function that we're talking about here is what initially sigmoid function was heavily used. It's still used, but not as proactively as it was used in the past. And what it would actually do is it would give you outputs like this. And so this is when we say, okay, it's binary, and we can define, okay, 0.5, greater than 0.5, we should say it's one class, less than 0.5, we can say it's another class. But what to do when you have multi-classes? So for multi-classes, another thing that came up was softmax. And what softmax would do is that it would try to find boundary between multiple classes instead of finding boundary between one class. And how that would work basically is that it would use the one versus all approach. So when you're training on one class, it would think of all the other subjects belonging to the negative class. So then it becomes a binary class, basically, a binary problem, basically. So here we want the triangles to be separated from everything else. So it's either triangle or it's not a triangle. So it becomes a binary problem. And similarly, then you are getting a combination of all of those boundaries, and you basically are able to separate when you combine all of these boundaries, you basically get that separation of all these classes. Now, moving on, we basically have neural networks, which form the basis of deep learning eventually. Now, what's the difference between deep learning and simple neural networks? It actually, as the name suggests, the only difference is actually in the depth. So the picture that you see above, where you just have one layer in the middle, you have an input layer, you have hidden layer, and then you have an output layer. That's where this is a simple neural network. But here you have more than one layer. So when you have more than one layer, no matter it's 2, 3, 300, 400, 1,000, whatever, it becomes deep learning. So whenever you have more than one layer in a neural network, it then is a deep neural network. So since we're talking about images and we want to talk about images, one of the initial concepts, now when we look at neural networks here, they would take data points one by one, right? So you could have like different data points here, different features here, different values going in. But in images, you basically do not have a 1D data. You have either 2D data or, it's a 3D data, but it's not 1D data. So what researchers did was they started using the simple neural networks or, deep neural networks for images directly. What they would do is that they would take the image, for example, this is an image with a 2D metric. They would unravel it, flatten it out, and so this would basically become 110, 421, and 021. And then since this is 1D, they would basically give it to the neural network. And that's how a lot of image classification in the start for machine learning was done, where directly the image, for example, we have this image, we have this handwritten digit, and if we zoom into this image, this is what we have. So we have values here, which are the different, grayscale values that we have. So values between 0 and 255. Since this is just a 2D image, no color. So we basically have values between 0 to 255 for each pixel. And then it would all be flattened out. And this is a 28 cross 28 image. So that when we flatten it out, it would become 784 pixels, right? So all the pixels total would be 784. And then that flattened out image would go into the neural network from pixel 1 till pixel 784. So this neural network input layer will have 784 nodes actually. So the cons of using this method for images was that it increased the number of trainable parameters for exponentially. So remember where we saw that all the W's and all the B's, those are the trainable parameters. And in that image, we were only actually looking at 3 input values. But when the input values are 784 just in the input layer, and your neural network will be according to that, then the trainable parameters would become a lot, which would take a lot of storage, take a lot of compute, would also be expensive, and not even that accurate. Now, why wouldn't it be as accurate as the CNNs or the special networks now are? That's because when we flatten it out and we'll give it to the neural network would not have any idea of what's the relation between pixel 12 and pixel 19, for example. Now here we know that this pixel 62 and 253, they are actually related because they're neighboring pixels. But once we flatten this out, we take that information away, and the neural network has no idea of knowing that, okay, these pixels have any relation to each other, or which ones are the neighboring pixels. So CNNs actually, what they did was that they would be fewer parameters, so it would be faster to train. They would reuse the kernel, detect feature anywhere. This is something that I'll explain in a bit. And then the architecture would also embed the knowledge of neighboring pixels. So before we jump into what CNN is, let's see how things were solved before neural networks as well, or side-by-side neural networks before the specialized CNNs came into being. So digital image processing is the concept that was being used heavily. And I think even in some cases, it's still used, but not that frequently anymore. And what digital processing would be that it would use image processing methods for different things. Now, image processing methods would be, for example, applying certain filters, smoothing and noise reductions, edge detections, contour detections, and all those things. So, for example, we want to detect the number plate on cars. So this is an original image of the car. So one of the things that we can do is, okay, we convert by digital image processing, we convert this into grayscale first, right? So we take out the color factor because that's not something that we currently using in the method. Then after grayscale conversion, we apply some noise removal methods, for example, the bilateral filter. So noise is removed and, a lot of things are smoothed out in this filter. Then we want to detect the edges. So we detect a couple of edges. And now we have this output that you can see on the screen. And now what we'll do is that we'll detect contours. So contours are basically the closed shapes that we are getting here. Could be, any kind of shape, but the closed areas that we are getting in this image. And we look for contours, which basically has 4 corners. So we're able to detect the number plate in this case. Obviously, this is not the best solution. And this is what we have followed: grayscale, noise removal, edge detection, contour detection, and then we are approximating. We kind of like, based on some rules that we have defined, for example, 4 corners, greater than certain area, maybe present in the lower half of the image, or we define some rules to make that approximation better, and then we detect this. But there are a lot of flaws in this approach. What if there are other rectangular shapes in the image? What if there's a board? What if the car is in the number plate is in the upper half because the picture is taken from a bit far, and a lot of those things, right? So it's not the best approach. And as you go through more data with this approach, there may be like a lot of cases where you're not able to detect the car number plate. And then for each case, you may think of, a new rule and add that to improve approximation. Then think of a new rule with some other problems that you face and then add. So it's like that iterative process where you're trying to figure out different rules and you're trying to generalize the system and make it approximate better. So the pros of these systems are obviously that you can run on any hardware, even on embedded systems like Raspberry Pi, Arduino, etc. It's fast, it works well on repetitive and monotonous tasks. Training is not required, which means that you just have a set of rules and you can have your system on the go. Cons are that it does not learn from the data, so it does not generalize well. You does not perform well when we have different conditions, for example, different backgrounds, different light conditions, difficult to utilize GPU with these algorithms, and then custom feature extraction. For example, in this case, we defined, okay, it should have 4 corners. It should have, maybe we say, okay, the color is white and things like those. So we do custom features. We think of these features to put. Multi-stage pipeline, you're performing a lot of different functions, a lot of different rules to get the answer. And then the kernels or filters that you're applying need to be hand engineered. So this edge detection, this is also a kernel, and this is also a kernel filter. And so when we say hand engineered, we're kind of saying, okay, we're defining that, okay, we're using a bilateral filter here, we're using an edge detection filter here. So we're defining those filters. And in a lot of more complex cases, you engineer those filters as well. Okay, what the values of those filters should be. So let's talk about what happens when we have colored images. So for example, we have no computers, we have nothing, right? But there was still color in the world, right? So what would you do to preserve a moment, right? Maybe you would have people sitting, and then maybe you'll have someone just paint them, and that was the way to have colorful memories or colorful moments captured, right? So you would have someone paint those things. And when we talk about paints, we have a lot of different colors on the palette, right? And not every color is always there on the palette, but the artist would mix different colors and they would create new colors. For example, if you see here, the artist mixed this color and this color to create this new color. So we have some base colors and we can combine them with other colors to create new colors. And when we are talking about initially just, for example, just black and white, then how do images look, right? So images would look complete, the pixels, you would have pixels and the pixel would either be white or it would be black. And a combination of those things, that which pixel needs to be white, which needs to be black, you would be able to get an image, you would be able to get an output, like in all of these cases. So if we increase, so image in itself is basically just pixels, right? It's a combination of pixels where different pixels have different values. When we talk about black and white black and white images, then we're saying, okay, you know, each pixel will either, it's going to be a 2D image, and second, each pixel will only have values between 0 and 255, like in this case. And then we have colored pixels, right? So we have colored images. There's one thing to note, however, and that is that the more pixels you have, right? This is 4x4, 10x10, 16x16, and you can see how it goes to 72 cross 72. And as you have more pixels, you are able to capture more information and you're able to see more definition of that image, because each pixel will only have one value, right? And when you have more pixels, you're basically able to define or pinpoint that position with that, you know, with a more specific color, with a more specific value, and you're able to have more definition in that image. So when you look at just this, you can see, maybe you can see, okay, you know, this is probably somebody, some eye, right? And this is actually a cat's eye. So if you zoom into this, you can see that, you know, each pixel has different values here. We have different colors that are coming in. And here is an example of two images or videos where one has more pixels and the other one has less pixels. And you can see the difference in the quality, right? And the quality with images with higher pixel, the quality is higher because each pixel can have more specific value, and that gives more definition to the entire image. Now let's talk about something called filters. So when we look, this is an image and it looks something like this, that it has half white and half black. In pixel values, it looks as you can see above. So you have values of 10, you have values of 0, and we can see that there's an edge here. Now, a vertical edge filter defined by these values, what it does is that it figures out where the edge is, right? And if you see this, then it has figured out that the edge is here. So it has figured out that the edge is here. Edge is at this center. So filters they work at the pixel level, and each filter, depending on, you know, what values it's carrying, has a different purpose, or picks out a different, or extract a different feature from the image. In this case, it was trying to extract the vertical edges from the image. So for example, if I want to detect horizontal edges, then I can just flip this filter and it would detect the horizontal edges if any horizontal edges are in the image. And if, for example, I want to get a plus sign from the image, right? So maybe I can use a combination of a vertical filter and a horizontal filter and apply both and then combine the results and then I would basically get the position of the plus in the image. So filters and combinations of filters, what they do is they're able to extract features from the image. So filters extract singly when they're used individually. They're able to extract smaller or simple features. But to get more complex features from the image, for example, a plus sign, you can combine the different features and their outputs and extract more complex features. And similarly, features in combination can be used to extract a lot more complex features from the image. So for example, this is the original image, and then this is what we get from the edges, and this is what we get with morphing lines. Then here, this is the picture of the moon, and after applying a filter, we are able to get these the moon in this shape, where we have the edge of the moon, and we have these different edges here as well. And here's another example of the input image and then the output of different kinds of filters on it. Another example of input image and the output of different filters on it. So let's talk slightly about images and machine learning. So when we have colored images, we basically, it's not 2D anymore, it's 3D. And at each position, we basically have 3 values, right? So for example, at the pixel 1 position, we would have 3 values, 4, 9, and 35, and combined, these would make a unique color. So this concept is similar to how painters work with combinations of different colors. So if you have red, blue, and green, what combination of each of red, blue, and green would make purple? What combination of red, blue, and green would make a yellow? What combination of red, blue, and green would make black? So different combinations of these 3 base colors would give out different colors in the output, and that's what these 3 values at each position are actually doing. So the third basically dimension comes from the channels, the 3 color channels. So, and you can think of this as that same image overlapped with 2 of its identicals, one in the blue channel, one in the green channel. So what kernels actually do is kernels convolve over the image and extract some feature from the image, depending on what the kernel, the values of the kernel. So remember that in digital processing, we said that the kernels need to be hand engineered. For example, we're already defining that this is a noise filter, and the noise filter has special values because of which it is able to remove noise. Similarly, the vertical edge detector has values in a certain form because of which it's able to detect the vertical edges. So these kernels are defined. But when we talk about computer vision and in machine learning, and when we talk about convolutional neural networks, they are based on the concept of convolution, where the kernel convolves over the image. But the interesting thing here is that the model learns the values of the kernel. And in one convolutional neural network, there are a lot of different kernels that are being learned. So the kernel values are learned by the machine learning model. And when we say that, we also mean that the model is trying to learn what features to extract, right? And the model learns by itself that what features need to be extracted. And then based on what features need to be extracted, it learns its own kernels. The convolution process, how it works is that you convolve the kernel over the image and you get an output. So if we see previously, so a kernel was convolved over this image to get this output. And then a kernel was convolved over this image to get this output. And a different kernel was convolved over this image to get this output. So depending on the different values of the kernel convolving over the image, you get different outputs. So this is how the convolution process actually works. So the green one is the kernel, and we have an image and it convolves over the kernel, and we get a different output image. So our kernel can also be a bigger. It's not always supposed to be 3 by 3, but it's usually always odd numbered. For example, 5 by 5, 3 by 3, 7 by 7. And here's an example of, convolution taking place over an image. So you can see that convolved convolution, the output of that came out in that one box on the right. So after this, I'll give an overview of how all of these different concepts combine in the architecture. But what max pooling does is that it picks the highest value, right? So for example, here's the image. And we have max pooling of 2 by 2, which means that, it picks one value every 4 pixels. So for the first 4 pixels, it picks the maximum value, 37. So the highest value from every block of 4. And then there's a concept of average pooling. The average pooling does, it picks the average value, calculates the average value for every 4 block and gives that as the output. So in the input image, then we have convolutional layers, and then we have max pool layers, and we have a combination of these in our CNN architectures. So in convolution layers, we are basically learning different kinds of kernels, different kind of filters, and the max at every, in every block of 4 pixels, it's picking up the maximum value. And combined with the convolution layer, what it does is that the convolution layer, the focus of the convolution layer is to pick out, good features, to learn good features, to extract good features from the image. And the max pool layer then further enhances that by picking the most prominent pixel value. And the second thing that max pool does, it quickly reduces the size of the image. So if you see in the previous slide, we had this input image, and this is what we get out of max pool. And it quickly reduces the size of the image while still keeping the important features in place, by still keeping a link to the important feature. So the feature that was learned by convolution layer. So because of this, the computation can be greatly reduced, because if we continue to just go with the convolution layer one by one, it would take a long, we have learned enough features, and then put that into a flattened layer and get the output. But with max pool, what happens is that it reduces the size of the image quickly, and the overall computation of the learning is reduced. Are working on the image. So at one point, multiple kernels, at one layer, multiple kernels are actually working. So these are different filters that are being run on that same So you can see that there are also in the same layer, there are a lot of different outputs. And then as we move on to the next layers, we have different kinds of outputs. So for example, when we give an input image, we have convolutional layers, then we have max pooling. So each of these layers that are tracked, each of these images that you can see tracked, you can think of them as an output of different kernel on this image. So for example, one kernel ran on this and you got this output that's in the front, then the second image, that was the output of a different kernel, and so on. So you can see that we're learning a lot of kernels as we are going down this path. And in max pooling, we're not learning anything. So those are not any learnable parameters, but they help to quickly reduce the size of the image. Then we have another convolution layer and then another max pool. So they're always, used in combination. And once we have, we've reduced the size of the image and we've learned enough features from the image, then we move it into a flattened layer and combine it with the output. So why this needs to be done is that the output, for example, in classification cases, and we're just talking about classification right now. So for example, I need to classify the data into, from 0 to 9. So my output layer would be a probability for each of these numbers, right? So whether this is a 0 or a 1 or a 2 or a 9. So if it's a 2, then the probability for 2 would be, for example, 0.9, and the rest of the 0.1 would be roughly distributed between the rest of the numbers. Point is that I should get highest probability for the number 2 here. Combining this output layer to the images which are still two-dimensional, and then there outputs from multiple kernels, and so a lot of channels behind it. So that is to flatten it when it, and then you basically have this layer where you're doing the final classification of what the image is. So a computer vision and CNNs have greatly, just jumping in a little bit into the AI consciousness of how the learning is happening. So for example, you have object detected, different objects with different probability values being detected here. And similarly here, you have different objects with different probability values being detected here. So what the model is learning at different layers, right? So the model learns very simple features at the start of the convolution layer. So the starting convolution layers of a network are learning the smaller features. And remember that I mentioned that kernels and their outputs can be combined to learn more complex features. So that's exactly what's happening here. So initially the kernels, they're learning very simple features around colors, edges, etc. Different kinds of edges, the different kinds of kernels. And as we move deeper into the layers, smaller features combine up to form more complex features. So you can think of moving down the convolutional layers or moving down these CNN network as drawing a bicycle, right? So when you draw a bicycle, you'll start off with simpler shapes. So you have circles, bigger circles, and different shapes are combining up into forming more complex weird edge shape that it needs to detect. That's neither vertical or horizontal, it's curved or anything else. So as we move from here to here, we are combining smaller shapes to make bigger objects, and then we're combining those to eventually get the final cycle that we want. So similarly, when we look at convolutional neural networks, in the initial layers, they are learning simpler objects. And as we move deeper into the layers, they're learning more complex objects. So in layer 5, you can see that the model has learned to detect people and cats and dogs, etc. And in the starting layers, it's just looking at colors and edges and patterns and textures. Here's another example of how layer 1 versus layer 2 looks like. So now that we have talked about convolutional neural networks, let's talk about how we can build one, right? So here you on the screen, you can see a very simple CNN network, and that has been created using TensorFlow Keras, which is a very simple, easy to use framework that you can use for building would be 3 by 3. So it would have 16 filters, and the size of each filter would be 3 by 3. Then we have the max pooling 2D layer, which here we have 2 by 2. So which means that it would be picking maximum value of every on 2D layer. And this time we have filters 32, kernel size 3 by 3. And we can see similar thing as we go forward. Max pooling is a way of compressing the image while enhancing the feature. When it's used in combination with 2D, it's very beneficial in the sense that it enhances the features that have just been learned by the previous convolution layer. You can see that here we have the flatten function. This is the function that then takes the 2D image or 3D image and completely the image that, you know, whatever output we have till here, it just flattens it out completely and then passes it to the rest of the network. The rest of the network is a simple dense layer, which is a neural network layer, which has 512 nodes. And then we have one node in the output, because in this case, we're just classifying classifying only 2 objects, so we can use then we know that it is 1 class, and if we get output close to 0, then we know it is a 0 class. So for example, if we are detecting horses, classifying horses and humans, so we can say, okay, you know, horses will be our class 0 and humans will be our class 1. Okay, so for some reason it's not downloading the data here, but let me walk you through the concept here either way. Because I think to get this result may take me more time. But what I'm doing here is that we have a data stored at this link. So I'm just using wget to get that data downloaded. And once this runs, you should basically, because you're defined that there's a temp, horse, and human here, so you should be able to see a zip folder here. So that's a horse or human zip folder here. When you have that zip folder, you can basically use the zip file library in Python to extract the information from the zip folder. When we use this, we basically call the .extract all function. We define this, and then we should be able to get the data extracted from our zip file, and should be able to see that. One thing that we can do is basically define the location of, since this this folder once extracted basically has 2 more folders in it, which would be for the horses and the humans. So we can define paths for each of those 2 folders. So here we're just using OS to join path with the horses. So now the location to my horses directory is here, and the location to my training human directory is here. So we can also use the os.list directory and call train horse directory, which is this. So what list directory does is that it returns you a list of all the files in that folder. And so this horse's name, this should have a list of all the file names in the folder. And when I get this printed with this colon 10, I'm actually printing just the first 10 files. And you can see the output of that here. So horses 26 PNG, 43 PNG, etc. And similarly for the humans file, you can see the outputs here. We can also print out the length of this list, and we'll know that how many files are present in each of these folders. So that's exactly what's happening here. So you're just doing os list directory, which will give the entire list, and you're just calling length on it. So that gives you the images in each of the folders. So we have 500 and 527 images respectively for horse and humans. So an interesting library to be used to explore different images in when you're using a notebook is basically matplotlib.image and using MP image in this. What MP image, you can just simply use basically to read a file. So what I've done here is I've just called mpread.imread, which is a function to read the file, and I've given it the OS, the path for the image that I want to read. So path where I have the train horse directory, and then which file I want to read from the directory. That is the list of all file names is in this. So I just want to read the 20th file in that. When you do plot.I'm sure this is what I'm getting. So this is a sample of the horse image, and then similarly we have a sample of the human image. So building a small model from scratch, that's something that we can use TensorFlow for, right? So let me import this. This should still work. Okay, and let's see how we can build a small model in TensorFlow. So the first thing that obviously that we need to do is define what our model will be. And since we are using TensorFlow as TF, so basically we'll just use TF to refer to TensorFlow keras dot models. And since we want this to be a sequential model, so one good thing about Colab, which I'm currently using, is that it gives you information on the different kinds of functions, and you have a lot of the libraries that are just pre-installed, so it just makes it very easy for you to learn and experiment with different kinds of models right here in the Colab. So I want my model to be sequential. And now you can see that as soon as I put bracket, it has started to give me information about what this basically does. So it creates a sequential model instance, right? And it also giving me the kind of input that goes in. So for example, layers and names, those things go in. So we'll create a list of layers that need to go into my sequential model, and this is what will define the architecture of my model. So the first layer that we want to add is the conf 2D layer, right? So now the conf 2D layer, and you can see that it's telling me that this is the order of whatever I need to add. So the first value should be of filters, then kernel size, then strides, if any, padding, so a data format, if there's any, and all of these different things that can go in here. So what for sure needs to be there is the number of filters. So let's start with 16 filters. We said the next is the kernel size. So we have 3x3 kernel size. We have our activation function because the activation, and remember that we talked that there was a sigmoid that was used a lot. So, and the activation function that's most commonly used nowadays is ReLU, and sigmoid is usually only used when there's any binary classification being done, right? In the layer that binary classification is being done. One additional thing that we need to have for the input layer, the first layer, is the size that would go in. So this only happens for the first layer and no other layer. Okay. So this was our first layer. Now the second layer that needs to be a max pool layer. So let's see. So we have layers again, right? Layers, and then we have max pool. Yeah, so we have all of these different kinds of max pool layers, you can see, right? So there's 1D as well, which is used for one-dimensional data. We have 3D as well. And we have a lot of global max pool as well. All of these have different functions, but what most commonly is used is the max pool 2D layer. So that's the one that we used and the one that we most well know the purpose of. So now we have our convolution layer and we have our max pool layer. So this was our first conv layer here. So let's create the second conv layer here. So the second conv layer would basically be all of this similar. So you have all of this. There's just one thing that will not be there. There will be no input shape because the input for this is the output that's coming from the previous layer. So the setting of what the input for this would be, that's something that the model fixes by itself, right? So the output here would straight up just go into this convolution layer. So we can keep the filter 16 or we can increase the number of filters. So let's just increase the number of filters and the max pool layer will stay the same. Then we can add a third conv layer. We can also just end the model here and we can add a flatten and dense layer, and then that would be our small model architecture. But it's good to have more layers in convolution neural networks, or at least a certain number of layers. So let me just actually copy paste that. So we can have 32 filters. There's no harm in having equal number of filters, or we can just have 64 filters here. Increase double the size of filter, right? So fourth conv layer. And let's just keep this 64. And okay, so I can either just end this here or I can have another layer here. So let's just have another layer here. And we have the same thing. Can make this 64. Okay, so now I want, this is all the conv layer combination that I want, and now I just want to end this architecture. So what I'll do here, I will basically have my flatten layer here. So that's the layer where everything will be flattened out. So you just call the flatten layer here. So after the flatten layer, because since everything is now flattened out, it's 1D, and the next layer that needs to be there is the dense layer, which is, you could say, neural layer, fully connected layer. There are multiple things that it's called. So we can have any number of nodes here. It's a different topic altogether to discuss how many nodes should be there, how many should not be there. Obviously, it shouldn't be very less because you're attaching an image that's flattened out to this layer. So it should have at least enough to be able to transfer the information that it's getting from the previous layer to the output layer and to learn better. So different numbers. So in this case, for example, we have 512 nodes. Again, for this layer, we need to define what activation function we're using. So in this case, we're using ReLU. And now the final layer, this is the output layer. Now here what we have a dense layer, but how many nodes should there be? This is important because this is highly dependent on completely actually dependent on the number of outputs you're getting, the number of classes you have. So in this case, we only have 2 classes. So we can use a single node and we can use the activation sigmoid. So in this case, we'll not use ReLU because ReLU does not give binary outputs. Sigmoid gives binary output. So that is why in this case, we will use sigmoid as our output function. So this is our complete layer neural network, CNN network. So we have 5 conv layers, and then we have a flattened layer. Then everything below this is actually called a fully connected network. So this is what was called the feature learning area, and this is the fully connected or the classification area. So we can also look into the summary of this. And the summary, when we basically call the summary, we can just use model.summary, and what it does is that you can see, for example, it tells you at every point the parameters at that point that are being learned, and the size of the image at every point. So you can see, for example, started off from here, but as you move, it's increasing, the channels are increasing, the size of the image, which started from some value is going to 33 by 33, 14 by 14, 7, 7, etc. And then at the end, it tells you basically the trainable parameters and the, that are there. So this is the number of trainable parameters that we have in this case. So how we call everything else in this function, remember we talked about optimizers. So you just do a TensorFlow, you basically do TensorFlow Keras optimizers, and you import what optimizer you're using. There's RMS prop, there's a stochastic gradient descent, there's Adam, and all of those have a different science behind them, a different approach that they're using to train the model. And some of them, you can say that some work better in some situations and some work better for some. But there's so many, and it's kind of like a hyperparameter, something that's in your hand that you can change and see, you know, which optimizer is performing better in which cases. Loss, we have binary cross entropy, and metrics, we have accuracy. And one thing that we have in Keras is basically image data generator. What image data generator does is that you can just you define it, and I've also defined additional things that I want the generator to do as it is reading the image. So the image data generator, as the name suggests, it generates the data for the model. So you give it a directory, a source directory, and it picks images from that and it gives it to the model. But you can also define some things that you want to do as it picks up the image. So for example, if I want to scale my images in between 1 to 255, 1 over 255. So what I would have to do is, you know, take those images, write a separate piece of code to do this. But I can just define it here and it would do it for me without changing the original images in the location, but just doing it on the run, right, as it reads them. You can also add a lot of other things here for data augmentation. For example, if you want certain images to be, you know, you want to add additional images for zoom factor, you can define the zoom factor, shear factor, and a lot of other things. So image data generator also helps with data augmentation on the fly. Once we have that defined, we just call flow from directory. We give it the input source. We tell it the size of the image. We tell what class mode this is. For example, it's binary. So it knows that, you know, there has to be just 2 folders there. If there are 3 folders, then you should likely see an error because we have defined that it's a binary classification. So it should only be able to see 2 folders there. If you say categorical here and you have 5 folders, so it will know automatically that there need to be 5 classes there, and it'll treat it that way. And once all of that is done, then you basically just call model.fit, and you give it the train generator, you tell it how many epochs that there need to be. Verbose one basically 1, 2, 3, we have different values and they define how you want to see the output. So for verbose one basically gives, for every epoch, it gives you the loss, the accuracy, and it gives you this progression bar as the model is training. So as the model is training, so the loss actually started from 0.81 and the accuracy started from 52%. But you can see that with every epoch, the loss eventually is decreasing and the accuracy is increasing, and it increases to 0.99 till the end. Since the data was very small and there wasn't any noise in the data, there wasn't much of those things, it was very small data, it was very you could say like a clean data. So the accuracy is high in this case. And but this also means that maybe since we trained it on very small data and a very clean data, it will not generalize well to, for example, completely unseen images. It may have overfit on this data. That's a possibility as well. But for this much of size of data and a simple network, this is a good accuracy per the epochs. So I guess I'm open to questions now, if there are any.
Thank you, madam. So that brings us to the end of presentation and hands-on lab session. So I would like now open the floor to questions if you have any questions. So please feel free to ask.
Madam, I have a question. What's the best way to get started with computer visions? And I want to know about any recommendations.
If you so do you already know machine learning, the basic concepts of machine learning, or do you want an advice on how to start in machine learning and then progress towards computer vision? So I'll answer the second one. I think that will cover both things anyways. So for machine learning, one thing is that you need to be good in Python. So if you don't know Python, then I would say that you start from there. Start with Python, learn Python so that you're comfortable with coding, and then jump into any of the introductory machine learning courses. There are many that you can take. There are also introductory courses on YouTube. And there are also introductory courses on Coursera. You usually get financial aid on Coursera for different kinds of courses as well. There are many courses by deep learning that even I have taken, before when I started my career. And I think they help a lot because they give you an overview of machine learning and then also help you with the assignments and how to create models, and you get comfortable with at least the model know-how. So so if you already know those basics, then maybe start off by taking a course that's specifically for computer vision. You should be able to find courses on Coursera, or you should be able to find deep learning .ai courses on computer vision, and or take a course that covers convolutional neural networks. I think there are courses on CNNs by deep learning.ai. Once you have that, or you're comfortable with any other course on YouTube or a course in Udemy, depending on the learning style that best suits you. Once you are comfortable with the different models and building models in CNN, you're comfortable working with a framework, whether it's PyTorch or TensorFlow, and then I would suggest that you work with different kinds of data sets. So for example, don't work with data sets from Kaggle. Pick any data set from Kaggle and try to maybe build a classification model around it. There are simple to complex data sets on Kaggle, so you can start off with the simpler ones. Data set that has, for example, for computer vision, you can start off with data set that does not have too many images, right? It has less images, about like less than 1,000, or maybe between 1,000 to 10,000, and then experiment with those and try to improve your model as you're creating model for those images, try to do some processing on those images, try to build models around it and improve accuracy. So once you'll, because that's practical data, once you'll work on that practical data, you will be able to see, learn new things. And as you do that, I think you will continue to progress in computer vision. And side by side, definitely start reading blogs. They help a lot. Be up to date with whatever is happening in computer vision, because there are a lot of different things, different concepts in computer vision. We've just covered classification, but there's, for example, there's object detection that is completely different, works very differently. Then there's object segmentation, there's instance segmentation. There are auto encoders, and even segmentation in itself. In segmentation, there are like multiple types of architectures, each work differently. Then there's masking, so like a lot of those things. Then there's generative models, the ones that, if you have heard about stable diffusion, or generating pictures from text. So like there are those kinds of models as well. So it continues to progress, but definitely the starting would be to get an understanding through a course or however, and then start practicing using data sets, public data sets, and then also side by side start reading blogs and learning about more complex models and then trying those out. A lot of those models are already they're open source, so they're on GitHub. So you have to basically, you can take those, learn to set up those repositories and build those models on any of your own custom data. Can you explain the roadmap for being a good ML engineer from a beginner? I think this is exactly the roadmap. This gets you started, and then obviously if you're on that roadmap to become an ML engineer, you'll probably also jump in for eventually a job in ML, and that's where you would really get a lot of practical experience. But I think continuous learning is the key to be. Reading blogs, staying up to date, understanding different architectures, that's what keeps you going. Computer vision, future of computer vision. What's the future of computer vision? A lot has happened in computer vision. So computer vision is pretty mature. There are a lot of things that are still happening. For example, now people are working a lot more on problems where you need both text and computer vision. So you need both NLP and computer vision, right? Stable diffusion is one of them, where you're giving text and you're getting an output. So you're already using both natural language processing and computer vision for building something. So definitely a combination of both those things does help. And I think moving forward, having an understanding of both sides would help. I would definitely suggest that it doesn't really stop at computer vision or NLP. I think the next big things that or the next job opportunity that'll be there will definitely be also in ML ops. So that's also an area to look into, but that would obviously, you will have a better understanding of ML ops when you have an understanding of computer vision and NLP and the basic core concepts. How will affect the AI tools like ChatGPT to programming jobs? I don't think it has that much of a big effect on programming jobs because ChatGPT cannot really build the system for you, right? But it can currently, I think it can really help programmers. For example, you want to you can ask it to write a function that takes a number of values and returns the sum. So it's just a simple example, but basically it would write it for you and give it to you. Or you can say, okay, you want to write a function that takes a point in XYZ axis and returns it in, I don't know, some other, it takes it in this plane, returns it, translates it by 90 degree, returns it in the other plane. So those things, so you can get it to write some functions, you can get it to write even more complex functions maybe, but the overall design of the system, the overall, okay, debugging things, patching everything up, building the product, that's still a programmer's job. So I don't think that's going away anytime soon. Can a fresher get a job as a ML engineer with solid knowledge on ML concepts but zero work experience? I think freshers should be able to get machine learning jobs if they have a solid knowledge on ML. I definitely feel that making yourself more visible always helps. Something that I understood a little late, but definitely have more stuff on your GitHub, right? To be able to show that you have a solid understanding of machine learning concepts. Be active on LinkedIn. Always look out for opportunities. Always look out for internships if you're still in undergrad. Pick good internships where you get practical experience, and keep your LinkedIn profile updated. And I think you should be good to go. But yes, visibility does help, especially, and of course you can also write Medium blogs. I think that's something that companies do appreciate when they're looking at different candidates. At least in Pakistan they do.
Do we have any more questions, guys? Okay, it seems like we don't have any more questions. So, okay, so we are coming to the end of the session. So I'd like to take a moment to thank our amazing speaker, Ms. Aqsa Kauser. Thank you so much for sharing your knowledge and taking the time out of your busy schedule to be here with us today. We all gained so much valuable insight and knowledge from your presentation. And I'd like to extend a big thank to our event coordinator, Huichi Man, for their excellent support in making this event a success. With that, we've come to the end of today's session. I hope you all found this event very informative and engaging, and that you all gained some valuable insight into computer vision. So keep learning and stay curious. We'll see you all at the next Pi and AI session. Thank you, everyone.
Thank you, everyone. It was a pleasure being here.